So we have a 0.15 kilogram ball on the end of a string. So our force should be tension and gravity that are working together or opposing each other for our centripetal force. The mass is 0.15 kilograms, radius 0.6 meters. It makes 2 revolutions per second, but our period, capital T, is how long does it take to complete 1 revolution. If it takes 1 second to do 2, it's half a second for 1 revolution. We're looking for the tension in the string at the very top and at the bottom, so we're going to set these up separately. We'll start with the top, and then we'll do the bottom. It always helps to start with a free body diagram, so I'll go ahead and draw a free body diagram for the top. When I'm at the top, my force of tension is down towards the center, and then mg, gravity, is always down. My net force equation would be I'm going to add those two forces together because they're going the same direction, and set this equal to MAC. Just like Newton's second law, summation of forces is mass times acceleration. This is circular motion, so it's equal to mass times the centripetal acceleration. Let's change acceleration to 4 pi square r over period square because we've got period and radius. So let's put it in terms of the variables that we have, and then subtract mg to the other side. So we have it solved for the force of tension. Now that it's solved for the force of tension and the variables are all the ones that we have, let's plug in mass at 0.15. 4 and pi square stay the same. Radius is 0.6. Period is 0.5. Don't forget that the period is squared at the bottom of that equation. And then we'll subtract mg at 1.5. When we do the math, we'll have 0.15 times 4 times pi squared times 0.6 divided by 0.5 squared minus 1.5. When I do that, I get 12.712 newtons. Doing it for the bottom, it's going to be very, very similar. The only difference is going to be at the bottom, tension is up, mg is down. We have to keep in mind that the net force has to be towards the center of the circle, so tension must be greater. We have to set it up as tension minus mg is our centripetal force, is equal to MAC. Net force is equal to mass times centripetal acceleration. We're going to rearrange so that we solve it for the tension. We're going to add mg to the other side and change acceleration into terms of the variables that we have. Acceleration is 4 pi square r over t square. Plug in the variables just like we did before. Mass at 0.15, radius at 0.6, period at 0.5, don't forget it's squared, plus mg at 1.5. Calculation's very, very similar as the one before, but instead of subtracting mg, we're adding mg. And I got 15.712 newtons. All right, going on to number 2. We have a girl on a swing set. You know, this regular swing set, you're sitting on like a little bench seat. There's 2 chains going up, traveling at 3 meters per second when at the bottom of the swing. We want to know the tension of each of the 2 connecting chains if they were 2 meters long. So our mass is 40 kilograms. Our radius is 2 meters. Our velocity is 3 meters per second. We have our givens listed out. It's always a good idea to go ahead and get a free body diagram going on. And then our net force equations, solving the problem. Easy routine keeps the more difficult problems simpler. To simplify it even further, I'm going to pretend like there's just one chain going up. I know that since both chains are vertical, they're going to share the force. They're going to share an equal contribution of the force. So if I treat it as 1 at the very end, then I can divide it by 2. So it just is simpler for me. So I'm going to say force of tension minus mg is equal to MAC. In this case, I'm going to change acceleration to v squared over r. I do that because that's the terms I have, the variables that I have, and v squared over r is acceleration. Once I've added mg to the other side, I can then put in mass as 40 times v squared. V is 3, so 3 squared. divided by radius. Radius is 2 plus the 400. 400 being mg, mass times gravity. 40 times 9 divided by 2 plus 400. When I did that, I got 580. That's the total force of tension up. I've got two chains. They're both completely vertical, so they're sharing that force. Because everything's balanced, there's no reason to think otherwise. Divide 580 into half. I get 290 newtons for each chain. Let's just keep it as simple as possible. Let's not overcomplicate anything. If it feels too complicated, it's probably because we're making it too complicated. Number 3, at what velocity would you be traveling to feel weightless? Okay, so we're looking for V. Feeling weightless, that means our force normal is 0. Remember, our perception of our weight comes from our force normal. If we feel weightless, we've got no force normal. Radius is 30 meters. Well, if our only force then is going to be mg, mg is our net force. It is our centripetal force. And centripetal forces are equal to MAC, right? The net force is equal to MA. Centripetal force is MAC. Okay, well, masses cancel out. Leaves us with G is equal to AC, but we need it in terms of V and R, so V squared over R. We're looking for velocity. Velocity is equal to the square root of RG. So the square root of 30 times 10. The square root of 300, when I did this, I got 17.321 meters per second. All right, front is done. Let's get the back done. A ball is swinging on a string, so it looks like tension is going to be one of the forces as a part of our centripetal force. What is the minimum velocity necessary? Okay, minimum velocity, that's one that we are learning and getting used to. Minimum velocity, let's just remember that square root RG. We've derived it a couple times in class and on this worksheet. Now this 80 centimeters for the radius, we don't do centimeters, we do meters, so we'll have to convert that. Let's go and get our formula written down, square root RG, and then the radius of 80 centimeters, there's 100 centimeters in a meter, so 80 centimeters would be 0.8 meters. So if velocity is the square root of RG, velocity would be equal to the square root of 0.8 times 10, or the square root of 8. And when I looked for the square root of 8 and got it from my calculator, I got the velocity is equal to 2.828 meters per second. Number 5, how much force would you feel against your rear end? All right, so it's talking about force normal. At the top of a roller coaster loop with a diameter of 15 meters, if your mass was 55 kilograms and your velocity is 15. Now, when you're at the top of the loop, you're inverted in this loop because you're inside the loop. So your force normal would be down, mg would be down, and at the bottom of the loop, your force normal is up and mg is still down because it's always down. We're going to set this up like we did on the front page where we've got the top set up separate from the bottom. If force normal is what we're looking for, we know the radius is 7.5, mass is 55, velocity is 1.5. At the top, if mg and force normal are going the same direction, so the net force is force normal plus mg is equal to mac. In this case, we want to change AC, the centripetal acceleration, to v squared over r because that's the variables we have. We need to convert it into the variables that we have. And we're going to subtract mg to the other side. So force normal is mass times v squared over r minus mg. 55 times 15 squared divided by 7.5 minus 550. When I put that through my calculator, I got 1,100 newtons. For the bottom, a little bit different. Start the free body diagram. At the bottom, force normal is up, mg is down. We know the net force has to be center seeking, so force normal is going to be greater than mg. That's what's going to keep you in that circle, taking you back up. So when we set up our net force equation, we're going to say force normal minus mg. They're opposing each other, opposing directions. Force normal is larger. is equal to MAC. Let's add mg to the other side and change acceleration into terms of variables that we have, v squared over r. Force normal is equal to 55 times 15 squared divided by 7.5 plus 550. When I did that, I got 2,200 newtons. Do not let this become an indication to you that the difference between the top and the bottom is a factor of 2. It worked out that way this time. It is not a consistent calculation. You need to work it out all the way. They're not going to be always twice the difference. We'll see. You saw that on the first page, right? All right, how many G's? How many G's does the writer experience? Take the force normal, divide by the mass. If you take the force normal and divide by the mass, what do you have? A force divided by mass is an acceleration. So if we divide by the mass and get an acceleration, G is 10. Well, how many 10s do you have in your acceleration? I don't know, divide by 10. So if we have 20 meters per second squared divided by 10, that is 2 G's because there are 2 10s in that answer, right? That's all it's looking for. So on the bottom, same thing. The force normal of 2,200 divided by the mass of 55. So the acceleration was 40. How many 10s is that? Well, divide by 10 because G is 10. That's 4 G's. Remember, 1 G is the one acceleration of gravity. Number 6, getting to the very end. All right, roller coaster engineer designs a roller coaster to the minimum safe velocity. What do we do with the minimum safe velocity or the minimum velocity? Velocity is square root rg, right? We're learning this, making it easier. Don't have to derive it every single time. So the velocity here is 14 meters per second. We're looking for the radius. So v is equal to the square root rg. If we square both sides, we'd have v squared is equal to rg. Divide g to the other side, and we'd get v squared over g is r. That's what we're looking for. And let's plug in some numbers. 14 squared over 10 is equal to r. 14 squared would be 196. Divide that by 10 gives us 19.6 meters for our radius.